This is a lesson on the polarization of light. So we've seen that light can do all sorts of interesting things. It can bend around obstacles, it can form interference patterns when it goes through slits, and it can split into different colors. We're now going to be looking at what physically happens to an electromagnetic wave when it passes through a specific material. Okay, we're going to look at polarization. So I'll start off with polarized light. Concept of polarized light. So polarized light is basically light with its electric field, so the component of the electric field oscillating along a particular axis or plane. And you can actually produce polarized light by passing it through what's known as a Polaroid, otherwise known as a polarizing filter. So light from the sun, from a light bulb, that's unpolarized light. Okay, it's got its electric fields pointing along random directions. You can actually polarize it by passing it through a specific material substance known as a Polaroid. Now, to polarize light, pass through a Polaroid, here's how you would do it. So suppose you have an initial electric field, so direction of incident electric field, E field pointing vertically up and down, as indicated by the arrows, and you pass it through Polaroid. So let's take this to be the polarization axis of a Polaroid. Okay, it's basically a sheet, a thin sheet of material. Now the component of the electric field that comes through, that gets transmitted, points along the axis of the filter. Okay, it's coming in at some angle. I should say it's at some angle relative to the vertical, where the hypotenuse is the initial electric field. This electric field component along the polarization axis can be expressed as E sub naught cos theta. That's the transmitted electric field. Okay, cos theta because you have adjacent, which is the dark red line with arrows, and the hypotenuse, which is the initial electric field. So the filter, the Polaroid, only transmits the component of the incident electric field that's parallel to the polarization axis of the filter. And from classical physics, we know that the intensity is proportional to the amplitude squared, right, of the light, where the amplitude is basically, if you remember, the maximum displacement of a wave from its equilibrium position. In other words, it's the maximum value of the electric field of the electromagnetic wave. And so we can rewrite it as follows. So I for intensity is proportional to the electric field squared, which in this case is the amplitude squared, and that's equal to, we'll just work that out up here, E sub naught cos theta. I should say E sub naught squared cos theta squared. And just to note, maximum transmitted intensity, I sub max, is given by E sub naught squared, okay? Because cos squared theta reaches the maximum when theta is equal to 0. All right, so when theta is 0 degrees, you get maximum intensity. In other words, when the electric field component is parallel to the polarization axis, you get maximum intensity. And so therefore we can write I is equal to I sub max cos squared theta, where I is the transmitted intensity, so the intensity that comes out of the filter up here, okay, the transmitted intensity. I sub max is the maximum transmitted intensity, and theta is the angle between the incident electric field, right, E sub naught, and the filter's polarization axis. This is also known as Malice's law. This is on the HSC formula sheet. Malice's law. discovered by Malus in 1808. Also, just to note, if you have unpolarized light, hitting a perfect polarizer, by perfect, it means that this means that half the light intensity will be absorbed into the filter and half the light intensity will be transmitted. Okay, it'll make its way through the filter. And this is because the electric field exists equally in all directions, okay, of the incident light. Now, in terms of the wave and particle models of light, Malus's investigation of polarization provided evidence against Huygens' wave model of light initially, okay, because compressed waves can't be polarized. Now, around the same time, a guy named Thomas Young, Englishman Thomas. Now, in terms of the wave and particle models of light, Malus's investigation of polarization provided evidence against Huygens' wave model of light, since compressional waves can't be polarized. Around the same time, a guy named Thomas Young from England worked on the double slit experiment, looking at double slit interference of light, and his work provided evidence to support the wave model. But he couldn't explain polarization, so he actually even wrote to Malus in 1801 explaining what was happening. And he proposed eventually that light waves are transverse and not longitudinal, contrary to Huygens. And around the same time, a guy named Fresnel in France also suggested that light waves are transverse waves. So let's see how Malus's law works. Let's do an example. Suppose we have unpolarized light coming in with intensity given by 200 watts per meter squared. Remember that intensity is power carried by a wave, okay, per unit area. That's perpendicular to the wave velocity. And power is measured in watts, unit area is measured in meters squared. So unpolarized light comes in and strikes a Polaroid. I should say the first Polaroid in our example. And then only a specific component of that light passes through, and then it hits a second Polaroid. And this second Polaroid is at 45 degrees to the first Polaroid, along the axis of the first Polaroid, first filter. Okay, and we're going to assume that the polarizing filters are perfect polarizers. Let's suppose we need to find the intensity of light passing through the first filter. Let's see how this thing works. Now, assuming that the filters are perfect polarizers, as we were given in the question, assumed in the question, we know that only half the intensity will come out, right? So half of 200, okay, the initial intensity is 200, half times 200 is 100 watts per meter squared. Okay, in other words, half the incident intensity is transmitted through the first filter. That's part A. Part B, suppose we need to find the intensity after the second filter. How do we go about this? Well, we need to use Malus's law. So Malus's law states that I is equal to I sub max cos squared theta. Okay, that's Malus's law. I sub max, we know what that is. That's simply the initial intensity, maximum intensity being transmitted. So that's 200 watts per meter squared, and the angle 45 degrees because the second filter is at 45 degrees relative to the first one. So it's 200 cos squared 45 degrees, and we get 100 watts per meter squared. And that's how Malus's law works, and that's the idea of polarization.